If the truck has a mass of 1.25 megagrams and the center of mass is at point G as shown on the figure, in order to figure out the greatest load it can move, if in one case the truck has a rear wheel drive where the front wheel are free to roll, whereas in part 2, if a truck has four-wheel drive, what will be that greatest mass? Additionally, we are given the coefficient of static friction between the wheels and ground as zero point 0.5, whereas the coefficient of static friction between the crate and the ground is given as zero point 0.4. In order to solve for that maximum load, first of all, let us consider the truck being a rear wheel drive. So first of all, we have to identify what is the tension that is being developed in the rope connecting between the truck and the crate. To do that, let us develop our free body diagram for the crate first. In this case, the crate has a weight of W, that is the unknown that we are trying to calculate, whereas the rope will always be in tension. That's why it is going away from the crate given by a variable T. Since we have the coefficient of friction between the ground and the crate of zero point 0.4, so we will have a frictional force opposing the tension force, so it is going towards the left hand side and its value will be equals to mu times n. In this case, mu value is zero point 0.4, whereas n is the normal force provided by the ground. Once we have the free body diagram, let us develop our equilibrium equations. So starting with summation of forces along the vertical y-axis equals to 0. In this case, we just have two forces. So our normal force N is equals to the weight of the crate. Whereas applying summation of forces along the x-axis equals to 0, the tension in the rope is equals to the frictional force of zero point 0.4 N. Next, let's develop the free body diagram of the truck here. Now, in this case, we will take the information of the tension, since the tension we have solved is equals to zero point 0.4 times the weight. So the tension force is going towards the left in this case. That is also showing that the rope is in tension as it is going away. Next, for the wheels, we will have a normal force represented by NA and NB, whereas the mass of the truck will be acting at the center of mass G, which value will be 1.25 megagrams times 9.81, and it is acting vertically downward. Next, since we are given that the front wheels are free to roll, there won't be any frictional force. Whereas on the rear wheels, since the truck is moving forward and the motion of the wheel will be in the clockwise direction, the frictional force will be opposing that motion and its value will be equals to mu times the normal force, whereas mu in this case is zero point 0.5. That is the coefficient of static friction between the wheel and the ground. Next, we also want to identify the distances so that once we are writing our equilibrium conditions, we can utilize these distances for the moment expression. Now, once we have the free body diagram that lists down all the external loads and the support reactions, let's go ahead and start applying our equilibrium equation. Now, to do that, we have three equilibrium equations starting with summation of forces acting along the y-axis equals to 0. Here I have two normal force NA and NB going in the upward direction, whereas the weight of the truck is going downward. That's why it is taken as negative. Next, I can write summation of forces along the horizontal x-axis equals to 0. So here we have the tension going towards the left. That's why it is taken as negative, whereas the frictional force of zero point 0.5 Na is going towards the right. That's why it is taken as positive. Next, we can simplify and represent our normal Na equals to zero point 0.8 times the weight. Finally, we are going to write our summation of moment expression. We can do at any point, but in this case, I'm going to select point A at the wheel, a rear wheel, so that we can eliminate a couple of forces, because once they are passing through the point, they won't create any moment. So starting with the tension force, it is going to create our counterclockwise moment with a moment arm of point 0.6, whereas our force, frictional force as well as Na, won't create any moment since they are passing through that point. The next force that will going to create the moment will be the weight of the truck in the counterclockwise direction, whereas the normal force at the wheel at point B is going to create our counterclockwise moment with a moment arm of 2.5. Now, in this case, we have three equations and three unknowns. We can simplify and solve for the weight here. So simplifying equation number 2, we can represent our value of NB in terms of the weight of the crate, that is coming as NB is equals to negative 0.096 W plus 7,357.5. Now, from this expression and the value of Na as zero point 0.8 W, we can plug these two in equation 1 and simplify and solve for our weight here. That is coming as 6,967.3 newtons. That is the amount of load the truck can move if it is a rear wheel drive. Now, next, let's move to part B, in which we'll see if we have a four-wheel drive, what is the total amount of load it can move. Now, at this point, I will ask you guys, let's make a guess. What do you guys think? Will the amount of load that this truck having a four-wheel drive will be more as compared to the rear wheel drive? And whatever your guess is, write in the comments, and then we will see at the end either it is higher or lower. Now, when we are saying that it is a four-wheel drive, the only change in the free body diagram will be now the front wheels are not free to roll, so there will be some frictional force present there as well. So just like the front wheels are moving in the clockwise direction, we will have a frictional force opposing that motion equals 2.5 times NB, while the rest of the free body diagram will remain the same. So once we have this free body diagram, again applying our equilibrium equation, having summation of forces along the y-axis equals to 0, we are getting as Na plus Nb minus the weight of the truck equals to 0. Whereas once we apply the summation of forces along the horizontal x-axis equals to 0, we have zero point 0.5 Na plus zero point 0.5 Nb minus zero point 0.4 W equals to 0. Finally, I'm writing my summation of moment at point A equals to 0. Again, the tension in the rope is going to create our counterclockwise moment with a moment arm of zero point 0.6, whereas Na, our F value of the frictional force on wheel A as well as the F value of the frictional force on wheel B won't create any moment with respect to point A as they are passing through the line of action of point A, whereas our NB is going to create our counterclockwise moment as well with a moment arm of 2.5 meters, whereas the weight of the truck acting vertically downward having a moment arm of 1.5 is going to create our clockwise moment. Adding them all up, their sum should be equals to 0. Now, in this case, I have three equations and three unknowns, so we can easily simplify this set of linear expression and get our value of load, that is coming as 15,328 newtons. That is way higher than our rear wheel drive.